Hey there, here we go into chapter 11. Very awesome stuff. This is the calculus of parametric and polar equations. So in this first lesson, we're going to talk about what I call the basics of parametric equations. So we're actually going to look at just how to graph parametric equations, what they're made up of, and how to do something called eliminate the parameter in a later video. Let's check this out. So number one, what is a parametric equation? Kind of written it out for you. What does it do for us? Parametric equations, they give us the ability to describe real-world situations, or non-real-world situations if you like, where the x and y values are completely independent of each other. So up until this point, you've had to plug in for x and get out y, right? So you've had things like y equals 5x squared plus 2. And you plugged in for x, let's say we plug in 1, right? So y equals 5 times 1 squared plus 2. Y completely relies on what we plug in for x. That equals out to 7. Now what we're going to talk about are functions where we have this t value known as the parameter. And so when we plug in for t, we can get out a separate x value than we do a y value. So the y value we get out does not rely on the x value we get out. They're completely independent of each other. The way I think of this is like with, if you've ever played with an Etch-a-Sketch pad or something similar to that, where you have complete and total left-right motion and complete and total up and down motion. That's what parametric equations do. You're moving independently left and right, up and down, and what happens when you put it together? Well, it's pretty cool. If you're just moving up and down like this, if you follow my finger, and then we also move my finger to the right, we end up with arcs, right? That's just one example. So left and right, up and down, and then if I move up and down and left and right, oh my goodness, we get different shapes. So complete and total independent motion, left and right, up and down, all based on a parameter. That's why we call it parametric equations. Now, if you're not digging that, that's cool. We're going to go over a real brief example of where this comes into play in the real world. So think about a ball in flight or anything just moving, that's been kicked or thrown, moves, generally speaking, in an arc, right? Especially with gravity. So something goes up and down, whether it's a soccer ball, a baseball, basketball is perfect for this, golf ball, and so on and so forth. So if you take any point in time, right, just kind of freeze the frame and say, okay, what's happening right here at this random point on this flight? You have two different things going on here. You've got the flight of the ball and how it's moving. Let's say that it's moving in this direction, left to right. So it's moving horizontally, right? It's flying this way. But it's also, believe it or not, moving up and down, right? It's completely moving up and down. So you've got a velocity moving in this direction. And in this case, you got a velocity moving upwards too, in this direction, right here like that, because it's moving up. And then here, let's say we have another point here. Here, we're still moving to the right, but now our velocity is moving down. So you have two different motions there. One is completely related to gravity, how gravity is pulling the ball down, right? So you kick the ball, put some kind of force on it, or hit it with a baseball bat, puts force going up. And then the force always pulling it down is gravity. And then we've got the fact that you also punted this thing or hit it with a baseball bat or whatever you did, a softball bat, and that directed it to go horizontally. So that's why it's moving from left to right. So you have those two independent velocities or movements. That's just one example of many. If you think about it, if you go running, try this. You go run, 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 and then jump. When you jump, you're pushing up and out, unless you're just pushing straight up. So you have those two different directions. Kind of cool. It's breaking down what we usually think of as one solid movement into two different movements, vertical and horizontal, y of t and x of t. Nice. I know, right? It's pretty sweet. Okay, so another example, and I think it's important to just go over these real world pieces before we go into the graphing, would be think about how you move throughout the day or a duck on a pond. So like let's say that you start out in your bed, let's say that's like here, and you walk over to your bathroom and then you change your mind, and you're like, I'm just going to go right back into bed. And then you get out of bed and you go on a different path getting out of bed. You go this way, you go down the hallway, and then you go down your stairs, I don't know, something like this, and you're doing all kinds of zigzag walking as you maybe go to your kitchen table and sit down for a little bit, and then move this way in the house. The point being is, that's a funky looking graph, unlike any function we've ever seen before because, well, it's technically not a function. But these paths exist in the real world. So how do we describe them with math? Parametric equations allow us to do that. right? Where if we're moving independent left and right, up and down, we can come up with shapes for anything. My face, your face, a toy, a keyboard, a penguin that you see at the zoo, whatever it is. A duck on a pond. Let's say you have a duck just kind of swimming around on a pond. Go to a pond nearby, watch a duck swim, right? It can go in all kinds of different patterns, making loops, right? Crossing over the same place many, many times. And the question becomes, how in the world do we end up with an equation for this? Parametric equations allow us to come up with a description of those movements. And that's really cool. So it's not just simple parabolas or cubic functions or sine and cosine functions anymore. When you split up things into x of t and y of t, you could graph anything you darn well please. That's sweet. All right, so how do we actually graph this? Let's get into the actual math of it and see that we've actually been here before. As I said, you've dealt with parametric equations, but not that you knew that they were parametric equations. So let me show you what I mean. You got the position of a particle that moves along the x-axis is given by this. So this, what we dealt with in the past, is considered rectilinear motion, with y of t actually equaling 0. What do I mean by that? Well, what we were mapping out in the real world is how we move along an x-axis, left and right, just like that, with no motion up and down. So that means that your y value was always 0 if you were on the x-axis. So as a set of parametric equations, you had the x of t value in terms of t, and y of t equal to 0. We're now going to plot all of this out exactly as the parametric equation is established. Before, we would usually graph out t on the x-axis, and the x value we got out on the y-axis. Now we're going to graph out the real-world motion just on the x-axis. So how do we do that? Well, you're going to find that graphing parametric equations is very simple. It essentially is just plug in t values and get out whatever the output is that we want. So I'm just going to pick a few. That's it. That's all there is to it. So we got t and we've got x of t. Y is always going to be equal to 0 because we're fixed on the x-axis. So I'm going to pick some negative values. Let's go like some random ones. I'll go with -3. We'll go with -2, -1, 0, 1, 2. We'll go with our typical ones actually. I'm not going to go -3. And we'll just plug them in. We'll get our values and we'll plot them. But we're just going to plot them on the x-axis because this whole time, technically, y of t is being plotted out. And that's going to be 0 throughout. All right, we're always going to be on the x-axis, no matter what t value we get. So when I plug in -2, I'm just plugging it into here. -2 cubed is -8. -4 times -2 is 8. Plus the -8 is 0, plus 1 is 1. So that's the point 1, 0 at time -2. Notice that the time does not get graphed here. So the point 1, 0, whoosh, right there. That's our first point that we're starting with, our first point. There's many more before it and many more after it. -1 we plug in. -1 cubed is -1. -4 times -1 is 4. And -1 is 3, plus 1 is 4. Oh, okay, so now we've moved to the right here. Interesting. And then 0, we plug in 0, 0 cubed, -4t, plus 1. Well, that's going to be 1 again. Oh, that's kind of interesting. So I'm going to plot that with a slightly different color. We've come back to that. So I'll go over the motion here because there's motion in these graphs shortly. And then we plug in 1. So if I plug in 1, 1 cubed is 1, -4 is -3, plus 1 is -2. Ah, so now we've gone to the left here and we're over here, right there. And then 2, when I plug in 2, 2 cubed is 8, -4 times 2 is, well, 0, because that's 8 minus 8, plus 1 is 1. We're back to 1 again. Interesting. Let's do one more, just see where we end up here. 3 cubed is 27, -12 is 15, and 1 is 16. Way out here. Okay, so what does this motion tell us? Because time doesn't really show up like visually, it shows up in the motion of things. We started at the point 1, 0, that was here. Then we went there, right? So that was our first motion. But then we kind of double back, right? So I'll do this in a different color. We doubled back from 4, and who knows, maybe we turned around somewhere over here. But I know that based on the points that we have here, we turn back around, go to 1, 0. And then we went to -2, 0, like that. And then turn back around like that. So we went to the right a little bit, slowed down, went to the left, and then turned back around, and that was it. Which makes sense. There were 2 turnarounds, which is what you would get in a cubic function that goes like that, right? Increasing, decreasing, increasing, increasing, decreasing, increasing. So that's pretty cool that the parametric shows up with our understanding of cubics. But that's it. It graphs out the actual path, which is kind of hard to see here because we're drawing it, as I said, rectilinearly, which sounds painful. It's Not as bad as it sounds. All right, so let's graph one more here. So it's time now for us to go two-dimensional. We're going to graph x of t equals t squared minus 2t and y of t equals t plus 1. We're going to indicate orientation on the graph, which means we're going to put arrows like we did in the past to show the movement. All right, let's do this. So I've got just a table of values. I'm not going to do as many values as that table might at first appear to have those values on. And that's going to be x of t. And I'll do enough room to, I guess, write out the function again. And then y of t. X of t we know is t squared minus 2t. We're just plugging in t values. It's super simple. Basic graphing 101. And so, I don't know, let's start with maybe -3. That's going to be somewhere off the graph, but we can deal with it. -2, -1, 0, 1, 2, and 3. And all we're going to do now is plug in t values into x and y, and those will give us the points. T does not get graphed, but we can see it come out on the graph. Let's see this. -3 squared is 9, minus 2 times 3 is going to be 6, and 9 is 15. -3 plus 1 is -2. This one's going to be really easy to calculate, right? Okay, so let's see. What else do we have here? We've got -2 plugged in is 4. -2 times -2 is another 4, which is 8. Plug in -2 and 1 is -1. And then we've got -1 squared is 1. And then this will be 2 when we plug in -1. Add that together, we get 3. -1 and 1 is 0. Then we plug in 0. That's going to be 0. This will be 1. Plug in 1. 1 minus 2 is -1. 1 plus 1 is 2. This one's going up by 1 each time, which makes sense. It's a line with a slope of 1, going up by 1 for every increase of 1 in the t direction. And then 2, we plug in 2. Squared is 4. Minus 4 is 0. Ooh, we're turning back around. Very nice, in the x direction at least. And then here, when we plug in 2, we get 3. And then here we plug in 3 squared is 9. Minus 2 times 3 is 6. It'll be 3. And maybe I'll go one more just for giggles. Just for giggles. 3 plus 1 is 4. And last but not least, 4 squared is 16. Minus 2 times 4 is 8. 16 minus 8 is 8. 4 plus 1 is 5. Okay, all we got to do now is plot the points. It's not bad. So 15, -2, that's way the heck off the graph here. That's right there. That's where we start. Then from here, we've got 8, -1. Okay, well, if I've got 8, -1, that's going to be here. Notice the direction's going this way. And now we've got 3, 0. Super simple. 0, 1. So that's going to be here. -1, 2. Ah, very nice. Starting to bend around. 0, 3. Bending back around there. 3, 4. That's up here. And last but not least, 8, 5. Beautiful. So now we're just going to kind of sketch this thing out. So to sketch it out, I'm not the best sketcher of graphs, but it's something like this as it bends all the way around. Let's try to get it through the points a little bit better. I think I could do better than that, right? Or maybe not. We'll see. All right, so we've got this arc right here going like that, bending back around like so. Now it says to give orientation, little arrow like that. You don't have to have 2 of them, but it shows that you're starting here and going there. And it makes sense. Break this into 2 different motions. You're moving bottom to top the whole time at a nice steady rate. Right? Just rising. That's what the y value is doing. The x value is moving to the left, right? We start out here at the right and it's moving to the left. Less and less x values, slowing down and then bouncing back out to the right. That's exactly what the numbers are doing, getting smaller and then bigger again. Smaller and bigger as we go up bottom to top. So that's like this. Break it into 2 different motions and it gives you 1 motion. So where does t show up in all this? Well, I mean, you don't graph it out. But here are the t values, just to kind of plot them out here. And what you might notice is there's more space between some points and less space between others. And that's interesting. We're going to talk about that just briefly here because that's going to be of import later on and understand things conceptually. So what does more space mean between 2 consecutive points? Well, if the same amount of time elapses between -3 and -2 and -1 and 0, let's say, but there's less space between here and there, we're traveling faster. That's what that means. So we're traveling faster. So I'll say traveling faster or at a greater speed. And if there's less space between 2 points, like here to here versus there to there, the same amount of time goes between 1 and 2 as does between 3 and 4, yet we've gone a lesser distance. That's a slower speed. So that would be traveling slower or slower speed. So traveling faster, traveling slower, however you want to think about it. That's it for graphing. It's very simple. Plug in the points, but there's a little more concept that you can intuit from it. And I'll leave it there. I'll see you in the next video. We're going to do something called eliminating the parameter. It'll be sweet. Peace.